Assalamu alaikum wa rahmatullahi wa barakatuhu. Welcome to Haseeb Electronics. Friends, in this video we will discuss all calculations to prepare a transformer, high frequency transformer. What is our requirement? First of all, to design a transformer, we have to calculate the outputs and what we have, what we need, what we have. In this video I will demonstrate if I have 24 volt source. From 24 volt source I want to make a circuit. I want to take 5 volt output, 4 ampere. For 5 volt 4 ampere from first output, first secondary, and it is center taped. We will use two diodes. Second secondary we need 12 volt 1 ampere and we use a bridge rectifier. And if we want to include one extra winding for regulation, for auxiliary, we can use this. We can consider this as auxiliary winding, or we can use another winding, so it will become in calculation. It is a push-pull topology. I am going to demonstrate this topology. Push-pull, center tape input, center tape output, and one extra output. So we can use the input. If we want to use a flyback regulator, we can use to half forward. If we want to use full bridge topology or half bridge topology, whatever we want to use, its factor will be added to selection of the core. In this video, in this calculation, we will use push-pull topology. Frequency 100 kHz and efficiency of the transformer we need at 98%. Regulation 0.5%. Diode voltage drop 1 volt for each diode. Operating flux density. For operating flux density, we have to refer this chart. Normally for ferrite cores, we use 2000 gauzes or 0.02 Tesla at 30 kHz, 35 kHz. We use maximum flux. When the frequency will increase, the Bmax will start decreasing. If I want to use 100 kHz, at that time it is approximately 1000 gauzes. But for calculation, first we will set 500. We will use this point to select core. How we can select core? First of all, we will select operating flux density BAC, alternating current flux density 0.05 Tesla. If you want to use in gauzes, you have to multiply by 10 raised to power 10. Core material, we want to use ferrite material. If you want to use a material, we have a ferrite material chart. At F100 kHz, there is low cost high power material, type of material and its specifications. We can use N27, N87, N97. For good magnetic index, we can use materials. Now, window utilization factor, we will set approximately, it is normal 0.3 to 0.4. We will set maximum with all insulations and everything. We will set it to 0.4 KU. And temperature goal when we will make a transformer, because transformer is calculated in worst case scenario with full readings, with maximum load current, with maximum losses, how much will the temperature rise? 30 degrees centigrade we will allow it. And maximum duty ratio, duty cycle maximum Dmax 0.5, 50%. Now we should remember to calculate a winding for center tape. We have to use 1.41. For single winding we have to use factor 1. This will be used in the calculation. I will upload all these pages in my Google Drive, and I will give the link so you can download the link. You can copy the link and you can download these papers from my Google Drive. Now we have to select a wire resistance ratio. We have to select wire. We have to consider a wire RAC or DC. DC resistance and AC resistance is 1. Resistance ratio RR is equal to 1. Now we have to select the skin depth. The maximum current flow at this frequency, 6.62 divided by F, and F we are using 100 kilohertz. So 100 kilohertz under root. So this is our calculation, kilohertz. 0.029 centimeter. This is skin depth. Because we want to select a core. Core is selected in 3 methods. The first method we can select by power handling. We can calculate the power and we need to go to frequency, typical power handling chart. So we can go to this number. Next we can find the part number of the core. 2 cores in PQ model or EFD model, we can find the number, frequency and power in watt. Under the frequency line we can select the nearest value. Then we have area product method, and the third one is kg method, core geometry method. How we can identify, how we can locate how we can select our proper core so that without losses we can transfer the flux from primary to secondary. Now when we find the skin depth, the wire we will use, it should be utilized fully, completely utilized. Now we have to define wire diameter, DAWG, because it is radius. So we can find 2 skin depth, then it is 0.4186 centimeter. This is our wire diameter. Then we can use, if we will use this wire, and when we will make winding, the stacks of the winding will leave some space, and how much the exact area of wire will be utilized, we have to find. Bare wire area, AW, is 3.1416 because it is circle, and wire diameter calculated. This is our bare wire area, 0.0137, the wire chart. In the wire selection table, AWG wire selection table, the wire area 04186, and the closest value, that is 40386. We need 0.04186 and we have 0.40386 in the diameter, because it is in millimeter. When we will convert it to centimeter, it will become 0.040. So we need 041. So it is very closest. And if we select this wire number, the wire gauge 27, its diameter is 0.36. The second thing, if we use wire gauge number 25, its wire diameter will 0.45. So it will thick. When this wire will thick, and it will not respond at maximum frequency. It is 85 kilohertz. We need 100 kilohertz. So our this range 100 kilohertz, and this frequency, this diameter is within range, and we can select the bare wire area. It is 00137 centimeter square. So it is 00128. It is mm square, millimeter square, bare wire area. So if we will select this will 25, it will go thick, and this is thin. So this is our required range. We need 0.0137 and we have 0.0128 because it is in centimeter square. When we will convert it, we have to divide it. For square we have to divide it by 100, so it will become 0.0128. So it is very closest. So we have to select wire gauge number 26. Wire gauge number 26. We should keep in mind this wire will fit in the window, and if we will select a thick size, because transformer, when we will select the core, we have a very small window here. This window area, we have to consider this. If we will use a thick wire, then it will cover a more area from this window. Window space we have to cover all the time. We have to keep in mind this window space. From this side we don't have any problem, but from this side, because when we will make stacks, we will make winding, so it will increase, and we have to put insulations. Then there is a bobbin, and bobbin and everything will cover this area. They will fill this area. We selected the wire size, and now we have to select the power output. To select a proper core, P out, power out, P out is equal to, because this time we have two windings, 1, 2, PO1, PO2, P01, P02. To calculate power, we know P is equal to V into I, voltage and current. So we discussed here, we need 5 volt, 4 ampere, but we need at this end. When this portion will work, we have to consider this diode. It will drop 1 volt. So 5 plus 1. If we will generate from here 6 volt, we will take 5 volt because it will drop 1 volt. And if we, in calculation, if we put 5 volt, then 1 volt will be dropped at this diode and we will find only 4 volt. So we have to consider this point as well. So we need in the output 5 plus 1 volt multiplied by 4, 6 volt by 4, 24 watt. 24 watt at this point. Now PO2, the same formula, output voltage 2 and diode voltage. Now here we have to consider another thing. When we need this point here, the voltage at this point, when the voltage will start from here, we will find one diode in this path, and in this path return line we have this one diode. When the polarity will change, this diode and this diode, so we need two diodes. One diode will drop 1 volt, and in the second line it will drop another 1 volt. So 1 plus 1, 2 volt, and we need 12 volt here. 12, 13, 14. 12, 13, 14. Pair of diode will be used in the output. So 14 volts. 14 volt multiplied by 1 ampere, we need 14 watts. So in the calculation, PO1 is here 24 watt plus PO2 14 watt, 24 plus 14 38 watt. 38 watt power is total output in the output area. Now we have to select apparent power, because here we are using two windings. So we have to multiply with factor U. With this factor we have to multiply it. PTS, PT secondary. In secondary apparent power, PT S01, PT secondary 02. So PT total apparent power 01 is equal to P01. What is P01? 24 watt. 24 watt multiplied by the factor for the center tape winding, that is 1.41. So total power in this area will 33.8 watt. The secondary number 2 are auxiliary winding. We can imagine this, or we can add one other winding in the same. How much windings we need, we have to calculate in the series. PTS 01, 02, 03, 04. If we need 4 windings, 3 winding in the output and 1 winding for auxiliary for regulation purpose, so we have to calculate in this portion. Just I am calculating 2 windings. So here PT secondary 02, P02, that is 14 watt multiplied by 1, because we have single winding, so it is 14 watt. Total apparent power is winding number 1 plus winding number 2, all portions we have 33.8 plus 14, 47.8 watt. That is apparent power. Now we have to total apparent power. This was only secondary. Now we have to total power from in the input side and output side. We have to calculate the total power. PT is equal to P in, input side, primary side power, plus P out. P in plus P out. P in is equal to P out over efficiency. As we discussed, 98% efficiency we need. We need 98% efficiency. So efficiency of transformer will added. If we will consider it as a 1, so input power and output power is same, so transformer losses, core losses, copper losses will be bypassed. So we have to calculate them. 38 watt is output power, and how much extra wattage should be added in the primary so that we will find this 38 watt in the output. So it will divided by 0.98 because it is in percent. It will 38.77 watt power in primary, and we have to calculate apparent power. To calculate apparent power, we have to multiply with the factor u, that is 1.41. So we will multiply 38.77 with 1.41, that is 54.67 watts. Total apparent in the input side and output side will be PT in plus PTS. PT primary, apparent power in primary, apparent power in secondary. Primary is 54.67 watts and PTS is 47.8 watt, which we calculated in step number 6. So the total apparent power will be 102.5 watts in the input side and in the output side. Now we have to calculate the electrical conditions KE to select a core. KE is 0.145, that is factor. Then there is KF, frequency factor. Frequency, Bmax or BAC or operating flux density, 10 raised to power minus 4. 0.145. Here is 4. Why this 4? This 4, if we are using pulse DC switching, our SMPS controller is here scare wave. So scare wave, in case of scare wave, we will apply switching DC voltage pulses. So when we use switching scare waves, we use 4. If we use sine wave for switching in the primary area, that time we have to use 4.44. Now it is 4. Frequency is 100 kilohertz. Bmax is 0.05 Tesla. It will become 5800 value. 0.145 constant for frequency factor. Frequency 0.05 Tesla, or we can say 500 gausses. Square, frequency square, KF square, 10 raised to power minus 4. When we will calculate it, it will become 5800. Now we can calculate core geometry, kg. For kg calculation, kg is equal to PT, apparent power, divided by 2 KE. KE is electrical condition and regulation. So 102.5 divided by 2, electrical condition KE, regulation, and it is 0.0177. Now we have to consider this, that this calculation, as we calculated the bare area of wire, when we calculated bare area, it becomes 0.78. It is ratio is for the actual winding area, and bare area is 0.78. And when we want to calculate it to make it 100%, we have to multiply with So when we selected PQ2020, it is datasheet for PQ course PQ2020. So this core, it have the ferrite core have this type of shape. Here are its dimensions. Here it is AE, effective core area. For this core, effective core area 62.6 millimeter square, and that is equal to 0.626 centimeter square, and area product, that is 0.408, and MLT, that is mean length turn. In the bobbin, how much the length of a turn will there, that is 4.4 centimeter. We can say it is the closest area of the core center area. When we will make first layer, second layer, third layer, it will expand. It is the mean length, the average length turn, that is 4.4 centimeter. And core mass, core weight is 15 gram. Its surface area is 19.7 centimeter. And window area is 0.658 centimeter square. Here is complete data sheet. I will attach this data sheet. Here it's weight and AE, effective cross-sectional area. So all dimensions are mentioned here. This method was used to select a core by core geometry. And if we want to select, then there is another method, that is WaAc chart. Then there is another method, core selection by WaC product. In this method, we take a window area and cross-sectional area. PT, apparent power 10 raised to power 4, BACF, frequency, current density J, or KF, frequency factor, KU, window fill factor. So after calculation, 102.5, that is our apparent power, multiplied by 10 raised to power 4, 0.005 Tesla, 100 kilohertz frequency, 433. 433 is current density. We will calculate it. I just show this formula. Multiply by 4 for pulse switching. 0.3 is window fill factor, and our area product will 0.3945. If we go to this chart again, if we use AP method, area product method, that is 0.408, and here is our calculation is 0.3945. If we use this AP method, area product method, window area and cross-sectional area product method, that is 0.3945, and in this way we will receive 0.408. The same, we will find the same core PQ2020. We have to select this core. If we are using the geometry method, core geometry method, that is 0.239. 0.239 is here. The same core will appear here. So in both cases, we have now three conditions. We can select core by core geometry method, window area, cross-sectional area product method, and simple power vs frequency method. Here is AP chart, product distribution WaAc chart. So this is typical power handling chart. We can select a core from this 100 kilohertz and our required power in output is 38 watt. So 38 watt, for 38 watt, that is in this range, so we can use this core for 2020 PQ 4 for ferrite material, 20 PQ 2020 ferrite material, or we can use in EFT, we can use 2523. These two cores we can select it. Now we are going to work on, now we selected PQ 2020. Now we can calculate the number of turns. For number of turns, N primary, V primary 10 raised to power 4, KF, BAC, FAC. KF is frequency constant, K, BAC Tesla 0.05, Tesla 100 kilohertz frequency 0.62, that is cross sectional area of the core, 0.62, that is in centimeter. So we need 19 turns, 19.35 the result, and we can select 19 turns. And if we want to verify the Bmax, because when we decrease the number of turns, the Bmax increases, the flux density will increase. So if we will increase more flux density, that time our core may be saturated, so we have to protect it from saturation. So verify Bmax 24 1000. Just only in this formula we have to put out Bmax and replace number of turns with Bmax. So Bmax outside, number of turns is in that place, so 19 here, it is 0.0509 Tesla or 509 Gausses. So that means we are in safe range, so our core will not heat up. The current density using window utilization factor at 0.29 or 0.3, J is equal to PT apparent power 10 raised to power minus 4, KF frequency 10 raised to power 4, current density PT 10 raised to power 4, KF, KU, Bmax frequency, and AP. So we can calculate it. KF is frequency factor. For DC pulses it is 4. KU frequency winding fill factor 0.29, because if we, for example, if we put 100 centimeters of winding and the working area of the copper will 0.29, it was, this factor will be multiplied by 0.29. So 29 out of 100 centimeters, 29 centimeters will working pure copper. Other the insulations and the gaps between the wires and everything. So 29.29 Tesla 0.05 Tesla 100 kilohertz frequency, 408 window area product WAC, this specification of the core 0.408. So current is 433 ampere per centimeter square. So current density in the complete winding will 433 ampere per centimeter square. Now we can use input current. Input current In is equal to P out. I is equal to P over V. So P out over V in multiplied by efficiency, transformer efficiency. So 38 watt is output power. And when we apply input voltage and we multiply it with 0.98, so our 1.61 ampere current will flow in the primary. So now we can calculate primary bare area. So AWP bare, In by D max, duty cycle maximum, that is 0.5%. We discussed in our first starting, we discussed maximum duty cycle ratio is 0.5. So 0.5 under root divided by 433 current density. So our primary bare wire area, is 0.00263 centimeter square. This primary bare wire area is 0.00263 centimeter square. Why we use this? It is to calculate the current handling capacity of the wire. Number of primary strands. What is strands? How much wires we need to join together to make them for full current flow. Number of strands, SNP. SN primary, AWPB primary bare area, AWPB divided by wire size, selected wire size. Selected wire size have bare area 0.0128. 0.0128. So 0.00128. So the result will come 2.05. 2.05. So that means we have to use two strands. We have by Riffler winding. We have to make a pair of winding to wind the primary winding. So for primary winding we have to make by Riffler winding, and it is center taped. We will discuss how to make a winding, but here we have to understand that we have to make a double wire in the primary. We have to calculate the primary resistance. So we have 1345 micro ohm per centimeter. 1345. Now because this is one wire, for 1 centimeter it have 1345 micro ohm. So when we will connect two wires in parallel, because now we are making strands, we are making as a loop, so it is in parallel. When it will in parallel, two resistor in parallel will divide it. So micro ohm per centimeter, number of strands 2. Our new value for 1 centimeter in the primary section will 673 micro ohm. One wire have this reading, but when we will use two windings, two wires in parallel, so this reading will come in micro ohm per centimeter. Now primary resistance, total resistance RP, primary resistance MLT. MLT is mean length turn. How much wire will used in one turn of the winding. NP, number of turns primary, that is 19 turns. Micro ohm per centimeter, this reading. Now we have to use this reading because it is new reading for our new primary. 10 raised to power minus 6 for micro ohm. So 4.4 multiplied by 9 MLT. MLT is in course specification that one average turn will take 4.4 centimeter wire. So 4.4 centimeter wire will be used in one turn. So it is very simple. Number of turns, wire in one turn multiplied by the reading, the resistance, it is total 0.0563 ohm, because now we converted it ohm. So now primary copper loss, we know the power loss PP, power loss primary, that is I square R. We know power is I square R. So I is maximum current flowing in primary. We calculated 1.61. Yes, we calculated the input current is 1.61 ampere in step number 13. So 1.61 square multiplied by this primary resistance. So our primary will lose power. There is copper loss 0.1458 or 0.146 watt. This watt will loss in the primary copper, the resistance of the copper. Now we have to calculate the secondary term. Secondary term same, NS1 secondary, we have two secondaries. So NS1 is equal to NP VS1 V in divided by V in. Now we have to calculate the regulation factor. 1 plus regulation, because it is in percent, divided by 100. So we said 0.5%. So when we will calculate it, it will come number of turns in secondary, because we have to add the regulation factor. If we will not regulate, if we will not add this feature, we will not get the regulated output. The output voltage will drop. So regulation factor, we have to add it here. 19 turns in primary, 6 volt in secondary. Why 6 volt? 1 volt for diodes. 19 multiplied by V secondary is 6 volt, V in is 24 volt, so 4.77. We can make 5 turns, because here we have to compromise it, because we cannot make 4.77 turns, we have to complete 5 turns. Now we can calculate the number of turns in secondary number 2, NP Vs2 divided by V in multiplied by 1 plus regulation factor, 19 turns in primary, 14 volt, 12 volt output, 2 volt for diodes, and it is 24 volt input, 1 plus regulation factor. We will use 11.1. We need 11.1 turn, but we will compromise at 11 turns. Now we have to calculate the same secondary wire bare area. I output D max divided by J current density J. So IO, we need 4 ampere in secondary number 1. Secondary number 1, 4 ampere, 0.5, it is 0.00653 centimeter square. Now we can calculate the number of strands, because we need 4 ampere. So when we use 4 ampere, so SNS1, AWS1 is secondary bare area number 1. So it will be divided by 26 number wire bare area. We know the bare area for 26 number wire is 0.00128. So it will be divided here in meters. So we have to use 5.1. Use 5 strands, 5 wires together, 5 wires in parallel. 2, 3, 4, 5. So we have to use 5 wires in parallel for wind or 5 volt 4 ampere, 5 volt 4 ampere. 1 centimeter wire have 1345 micro ohm in 1 centimeter. So when we connect 5 wires to make winding of secondary number 1 to take 4 ampere, so for taking 4 ampere we have to connect 5 lines. So when we will apply 5 wires, when we will connect 5 wires, the total resistance will decrease. How much it will decrease? Micro ohm per centimeter, number of strands 5, it will become 269 micro ohm per centimeter of every centimeter in the S1 winding. So total resistance for RS1, number 1 winding in the secondary, MLT into NS1. MLT is mean length turn, average turn length. NS, number of turns in secondary, micro ohm per centimeter, multiplied by 10 raised to power minus 6 for convert into ohm. 4.4, that is average ratio in the core data. Number of turns 5, 269 we calculated now. This value 269 will added here. It is 0.0059 ohm. So when we know the value and we know the current, resistance and current, we can find P is equal to I square R. Power loss in secondary number 1, PS1. So 4 square, 4 ampere current it will flow in the secondary number 1, and resistance it will 0.0944 watt. Now we can calculate the bare wire area of winding number 2. The same formula, IO2 Dmax duty cycle maximum divided by J current density. I is equal to 0.5 divided by 433, and we can take this value 0.00163 centimeter square. This is AWS2B, bare area. Now number of strands in secondary number 2, SNS2, AWS2 divided by 26 gauge bare wire area, we have 00163, it is 00128. The result will become 1.27 strands, and if we will use one strand we cannot take 1 ampere, so we have to use 2 strands, 2 wires in parallel for winding. For 12 volt winding we have to use 2 wires in parallel. The same micro ohm per turn 1345, and we are using 2 wires in parallel, so resistance is 673 ohm micro ohm per centimeter. And resistance, total resistance in secondary winding number 2 for 12 volt winding, MLT NS2 micro ohm per centimeter, and it is 0.0326 ohm. Copper loss in secondary number 2, PS2 I square S2 RS2. So we have 1 ampere. We need 1 ampere multiplied by 0.0326. So it is 0.0326 watt. Total secondary power loss. We calculated the power loss in first winding and second winding. Power loss in primary, that was in step number 24, it is 0.0944 watt. 0.0944 watt in 5 volt winding, and the second winding, that is 12 volt winding, it is making loss 0.0326 watt. And total loss, power loss in the primary, copper loss in the primary, that is 0.127 watt. Now we can calculate the primary and secondary power loss. PCU, total copper loss, we calculated in primary. In primary we calculated power loss is 0.146 watt. 0.146 watt. And in secondary we have loss 0.127. So our total loss in the copper winding 0.273. And if we use some other winding, some other material, then this winding loss will increase. Now we can calculate the regulation. Losses divided by power out multiplied by 100. So power loss is 0.273 divided by 38 multiplied by 100, it will become 0.71%. So it is our regulation. We assumed that we need regulation 0.5%. It was our goal, regulation 0.7%, 0.5%, but after calculations 0.71% is very close to 0.5%, so we can compromise here. Now milliwatt per gram for ferrite material. It is calculation for PC44 material. For ferrite material PC44. If you will use another material, you have to consult the data sheet to find this milliwatt per gram core ferrite loss. Ferrite material, how much it will make loss, we have to calculate it. F frequency, we have to power 1.51, and flux density 2.747. After calculation it is 3.01 milliwatt per gram. The mass, the weight of core material, and core power loss, how much PFE milliwatt per gram, that was copper loss. And here it is core loss. Core loss MWG WFE, weight of ferrite core 10 raised to power minus 3 milli to watt 3.01 multiplied by 15 gram multiplied 10 raised to power minus 3. It is to convert into wattage. It is 0.045 watt. So now we will calculate total losses. Total loss, PCU, total copper loss, and total core loss 0.273. It was our copper winding loss in primary and secondaries. 0.273 plus 0.045, this ferrite core loss, total 0.318 watt will dissipated in the core and in the winding. If we will increase the Bmax, flux density, at that time our turns will decrease. When turns will decrease in primary, in secondary, that time the copper loss will increase. When the copper loss will increase, the core losses will increase. So here we can calculate watts per surface area. So total power losses and surface area. Surface area is 19.7 centimeter square and total losses are 3.18. So our every square centimeter will dissipate power 0.0161. that is very safe. Then we have temperature rise. Temperature rise 450. Temperature rise will be calculated 450 multiplied by watts per surface area. Watts per surface area, and it will be powered multiplied by, it will be squared by 0.826 450, and our per unit area 0.016 watt per centimeter square. So the maximum temperature rise at full load will 14.9 degrees centigrade. That is very safe. Our goal was, maximum temperature goal was 30, and total windows utilization KU, how much window will be utilized, KU is equal to window utilization in primary and secondary. So now we will calculate for the secondary NS1 SN1 multiplied by bare area divided by window area. NS1, number of turns in secondary number 1, that are 5 turns. But remember, now we are using center taped winding, so 5 plus 5, 5 plus 5, 5 turns here, 5 turns here, so we have 10 turns, and we have 5 strands to take 4 ampere in the output, SN1 and AWS1 wire bare area, that is 00128, and it will be divided window area, it is 0.658 centimeter square, 0.658 centimeter square, it is in the core data sheet, 0.0973. For secondary winding we have just only single winding, we will use 11 turns, 2 strands, 2 wires in parallel by riffler winding, core bare area, wire bare area divided by window area, it is 0.0428. KU primary 38, because 19 turns in one portion, so we are using center tape, 19 plus 19, 38 turns by riffler winding, 2 strands, 0.00128 divided by 658, it is 0.148. So here KU, total window space, window utilization, KU primary, KU secondary, 0.148 for primary. For secondary number 1, secondary number 2, utilization is 0.288. KU is 0.288. That means our winding is perfect in the window, because we assumed our goal was window fill factor 0.4, so we are within the range. So I will upload these papers and all data sheets in my Google Drive as a PDF file. You can download it and you can calculate them. It is very useful method to calculate of core by using core geometry method, KG method. This one is KG method, and next we will use window area, core area product method. That is also, the basic technique is same. The calculation will remain same, just only the core selection method will be changed. From first to end, all the method will same, just only the core selection method will be changed. So I hope so this video is good for you. If it is good, like, subscribe, share, and if you want to watch my future videos, you can press bell icon button. Thanks for watching. If you have any question, please let me know in the comment box. Assalamu alaikum warahmatullahi wabarakatuh.